This video presents an introduction to the multiple PTF modeling framework. This is where you like to model multiple triangles. Typically, it will be multiple incremental paid losses. And the MPTF modeling framework, as you shall see, is extremely powerful and flexible. You can even use it just to manage, say, 25 lines of business, even if you're not interested in the correlations between them. So instead of running a model for each line, creating the output and the report for each line, you could use the MPTF modeling framework just to manage those 25 models by designing a composite model with zero correlations. That composite model essentially is just the corresponding model, identified model for each line. And when you run that model, you are in fact running the model for each line. You get the output for each line and the aggregate and so on. It's a great way for just managing various parts of your business, even if you weren't interested in the additional output in terms of diversification, capital allocation, and so on. Another application of the MPTF modeling framework is multiple segments, like medical versus indemnity. They're usually correlated, same line, different states. Gross versus net of reinsurance. So it's gross data versus net of reinsurance data. This way you can also find out whether your retained, whether your outgoing reinsurance program is in fact optimal in terms of reducing the risk. Layers, including high severity, low frequency, credibility modeling. You might only have a few years of data available, so it's a small triangle. There's another same line of business, perhaps written in a different state. So let's suppose this line is casualty treaty, where you have a big triangle. You've written it for more years. You can sort of borrow strength from the big triangle to model and estimate the parameters for the smaller triangle, especially the development out here, which you might obtain from the information in the bigger triangle. You might have a triangle that has a lot of process variability. It might still be a large triangle, and when you estimate the calendar year trend due to a high process variability, you don't have a very precise estimate of that trend. The wizard might set that trend to 0, but when you re-estimate it, it might be 5% plus minus 4%. And you could argue due to the high process variability, there is a trend, but I'm not too sure what it is. So based on the information on this triangle alone, you would just project with a 5 plus minus 4% trend, meaning that the true trend is a random number from a normal distribution with mean 5%, 4%. You might then have the industry data, and you might be able to credibility adjust that trend, get more information, a more precise estimate of that trend using industry data, only if there's some kind of correspondence. You do that statistically informally. I mean, if the trend in the industry is very different, then there won't be any adjustment. Another application of the MPTF is breaking up a triangle. Now, what does that mean? You might have a change of mix in risk between this accident here and that one. And as a result of that, this inflation might not be, this iota might not be the same as that one. This development here might not be the same as that development. So what you do, you break up the triangle, decompose it into two triangles. That part has got, this triangle's got data here, but all these numbers here are 0 with very small exposures relative to these exposures. Whereas for this triangle, all these numbers are 0, and this part of the triangle is the data taken from the bigger triangle. So the sum of the two triangles is in fact equal to the bigger triangle, but when you model in MPTF, you could test whether this inflation parameter is the same as that one, whether this development here is the same as that development there, and so on. Is the process variability the same in this part of the triangle as it is as that, as a result of change in mix of risks? In fact, some of the diagnostic testing of the parameters can actually be done in PTF, but more formally in MPTF. So it could be change due to change in mix of business, mix of risks, different development, different inflation, might be different process variability. Another application of MPTF is modeling or finding the reserves for different layers for different accident years. So what you would do is you would create, let's suppose there were only 2 layers. It's limited to $100,000, limited to $200,000. You create the 2 triangles where the paid losses are respective individual losses limited to 100K, limited to 200K, and then these will be very highly correlated because they're parts of each other. You'll do in MPTF, you find the relationship between the 2 triangles, you design a composite model, and then you do your forecasting, and in PALD you could do the simulations for every cell, and you could then create a composite triangle, say in Excel, where you take these simulated values and put them there, you take these simulated values and put them there, and you take these simulated values and put them there, and so on. And when you look at this composite triangle, or actually it's a rectangle in this case, any calculations based on these simulated values in Excel will be in terms of different layers for different accident years. Of course, if you had more than two layers, you would do this. You go for the same process. Okay. So what we're going to do now is if we go and open workbook 104A, and we might go to the variable, perhaps multiple. Let's do that, multiple LOBs. And you'll see one called LOB1, so you highlight that one, Control key and your mouse button, and highlight, oops, can't find it. Okay, it might not be here. LOB3 might not have the variable assigned to it. So what I'll have to do is go back there, search for LOB1, there it is. And LOB3 is actually next to it. In fact, one thing you could do now, you could just highlight LOB3, assign values. You could go to multiple, assign LOBs. Now go to multiple LOBs, and LOB1 and LOB3 are there. Highlight those with the right button of your mouse, open them. Now tile vertically, minimizing database view. Now, one has a model called Good3, run it, double click on it. LOB1 has a model called Good1, double click. Then tile vertically, minimize regression tables. Let's look at the model displays and the residual graphs versus calendar year. Okay, for LOB1, remove the parameter from 98 to 2000. Just remove it. Click on it to estimate. And what you find now is that each line of business has a new trend in the calendar year 2000. So each line of business has a 0 trend to the year 2000, then a positive trend starting in the year 2000. Line of business 3, LOB3, 0 trend till 2000, then a new trend. Now, just make active one of the residual graphs, so click on it, and then tile vertically, minimize other types. So we're only looking at the residual graphs. And you'll see that in each one, if I look at the one on my left, from 98 to 2000, the residuals go down, then they go up from 2000 to 2002, and then it flattens out. That's for LOB1. LOB3 seems to do sort of kind of a similar thing. 98 to 2000 it goes down, 2000 to 2002 up, and then down. So there seems to be what we call a little bit of process correlation. The residuals are correlated. What does that actually mean? It kind of says that if the two lines were independent, then a residual is either positive or negative with equal probability of 50%. Either the number is above the trend line or the outcome is below the trend line on the log scale, 50% each way. But now that you've got process correlation, and you'll see we'll estimate it in a moment in the MPTF module, you actually find that now you're actually going to argue that if in one line of business a number in a particular cell is above the trend line, the probability that it is above the trend line in the other line of business in the same cell will be more than 50%. So let's now look at correlations in our PowerPoint display. And so we've got our two lines of business. We've got these correlations. What we have now is actually two equations, and these residuals are correlated. And in the next video, when we go into the MPTF modeling framework, we're going to use the fact that the residuals are in fact correlated. And if the residuals are in fact correlated, you'll see that when we estimate the parameters for the first line, say, for this data set, we'll use the data for the second data set and vice versa, which we'll cover in the next. Let's talk a little bit about correlation and linearity now. Correlation, linearity, multivariate normal, weighted least squares are all the same concepts. So let me just illustrate this graphically. Suppose you're looking at two variables, and x could be height, and the y's values could be weight. So this is y, and on the right x-axis we have x. And suppose you look at the population of people who have a height between 172 and 173 centimeters. So this is a subpopulation of weights. All those people have a height between 172 and 173, and you draw a frequency plot of their weights, and it happens to be normally distributed. So here's a normal distribution, and it has a particular mean. Now you look at those people who have a height which is around 180 to 181, so it's a subpopulation of weights, and you look at their frequency plot for their weights, it's also normally distributed. But it's got a higher mean. But it's got the same variance as this subpopulation. And then you go to a different height, and it happens you also have a normal distribution. So every subpopulation of weights has to have, based on height, has a normal distribution of weights. The mean of the weights, in fact, is linear in height, but the variances of the distributions are the same. Now, it turns out that there is a distribution that has these properties where the subpopulation of y values based on heights are all normal distributions, and the mean of y given x is linear in x. But also you'll notice that the variance of y given x is constant. The variance of all these subpopulations is constant. So if a random variable y and x have a joint bivariate normal distribution, then the expectation of y given x is alpha plus beta x. The variance of y given x is a constant. It doesn't depend on x, as you can see in the phenomena that we might find in weights versus heights. And of course, y given x is normal distribution, where the mean is linear in x. It turns out that correlation is a statistical definition. The correlation between the linear correlation between two random variables has this. It's a formula, okay, and it measures actually a linear association between two random variables. Remember, linear association. In this bivariate normal distribution model, on this linear regression model, the coefficient beta, the slope of this line, beta, is equal to the correlation coefficient, the standard deviation of y, the standard deviation of x. The standard deviation of y is not the same as the standard deviation of y given x. The standard deviation of y will be the standard deviation of all possible weights, irrespective of heights. So that's going to have a big standard deviation. The distribution might look like that. It's normally distributed, but it's got a huge variance. The variance of y given x is much smaller. That's the variance of subpopulations based on height. So this is a formula. Now, if the slope of the line is 0, beta equals 0, the correlation is 0, and vice versa. If the correlation is 0, the slope of the line is 0. So this is why in the usual regression model we write y equals f plus beta x plus an error term. This error term is an integral part of the model, and it has a normal distribution with mean 0 and say variance sigma squared y given x. It's a constant variance, and the variance doesn't depend on x. However, not all variables are linearly related. Suppose we have two random variables related by the equation s equals t squared. If t is normally distributed with mean 0 and variance 1, what's the correlation between s and t? Well, s is a function of t. It's a quadratic function of t. And a lot of people would say, look, they must be very highly correlated. Indeed, the correlation is 0. And the correlation is 0. The covariance is 0. Between s and t is 0. Well, because the relationship between s and t is far from linear. It's a quadratic. Remember, correlation measures linear association. In fact, the only time the correlation equals 1, if you've got two random variables, the correlation equals 1 or minus 1, if and only if you can write y equals alpha plus beta x. There's no error term. In other words, one is a linear function of the other. It's the only time correlation can be plus 1 or minus 1, provided the random variables have got second order moments. Okay. Linear correlation is a measure of how close two random variables are to being linearly related. As I've said before, if the correlations are the 1 and minus 1, one is a linear function of the other. If y and x are linearly related and f and g are functions, the relationship between fy and gx is not necessarily linear. So we should not expect the linear correlation the same as between y and x. And that's very important when you look at normal distributions and log normal distributions. The relationship between normals and log normals. Let's suppose we have two normal distributions without, any loss, without loss of any generality. We can assume each one has a mean of 0. So one has a standard deviation sigma 1. The other one has a standard deviation sigma 2. So two normal random variables, each has a mean of 0. Okay. You know that the mean of the corresponding log normal will be the exponential of a half sigma 1 squared. The other log normal will be the exponential of sigma sub 2 squared. Okay, so excuse me, sorry for that phone interruption. Okay, so we know that the mean of the corresponding log normal does depend on the standard deviation or variance of the normal distribution. It's the same with the correlation between, if you've got two normal distributions with a correlation, say, of 0.78, so rho is 0.78, the correlation between two corresponding log normals, well, first of all, it's not linear, but if you measure the linear correlation, it keeps on changing depending on the sigma 1 and sigma 2. So if we start off with a correlation between two normals of 0.78, these are just simulated random numbers of say, y values versus x. which are have a bivariate normal distribution. The standard deviation of y is sigma 1. The standard deviation of x is sigma 2, and there's a fixed correlation of 0.78. If you now make the standard deviations of y and x equal to, say, 0.1, and you simulate, and basically you're exponentiating the y and the x, and you do a graph of EY versus EX, so this will be EY versus EX. It looks like that. But when you increase the sigma 1 and sigma 2, it starts looking not particularly linear, and that's what it looks like if sigma 1, sigma 2 is pretty large. So the linear correlation, using that formula, rho equals the covariance divided by the respective standard deviations, it doesn't look linear anymore. In fact, here's another example. Two normals, and that's what the two corresponding log normals actually look like. But all the analysis we do is on a log scale, and we always check that we have normal distributions, and then the correlation we measure, in fact, is a linear correlation. And then after doing all our projections on a log scale in terms of multivariate normal distributions, we use the relationship between multivariate log normal and its corresponding multivariate not normal to produce all the projections for each cell. The projections are all log normal distributions. Okay. I think that's the end of this particular video. Yep. Thank you.